Unit 8, Atomic Theory, Lecture 3. We'll continue the development of our model by considering the Aufbau process, and in this we will talk about ground state rules, electron configurations, the Pauli exclusion principle, some important exceptions to the Aufbau process, and we will conclude with electron configurations of ions. Ground state rules. Now, the Aufbau process is really a method of describing the electron configurations. We give you a series of rules or directions to help you do this, and it is describing the electron configurations of our model of the atom. And we use it mainly for ground state electron configurations. What do we mean by this? These are those electron placements that deal with the lowest possible energies of the electrons. Fill the lowest energy level first. Start at the basics, start closest to the nucleus and work out. Do not permit more than 8 electrons in the outermost N. There are exceptions. You need me to slow down a little so you can catch up? The next rule is Hund's rule. Place 1 electron in each orientation singly before pairing. Now, if you have a hard time getting a handle on that, I'll show you what we're talking about. 1 electron in each orientation singly before pairing. Now, this next is really a general observation, but we find that filled, half-filled, and empty energy levels are usually best. Is it because they have better symmetry? Well, I don't know. And this is not actually a part of the Aufbau, but it will help you to understand, or it'll help you to find a way to look at some exceptions that we'll deal with. Do you remember this table? Yeah. Okay. Keep this in mind, keep it at hand, and let's go. Let's start out doing our electron configurations by using hydrogen, the smallest atom, with a symbol of H, and we know it has 1 electron. Where does that electron go? It goes into the 1s, and there's 1 electron there. Are you confused? Do you need to see that table? Here it is. N is 1. See, we go into the lowest level of N that's available. And the shape is S. And we put in 1 electron, can hold 2. Well, what are the 4 quantum numbers for this 1 electron? In other words, what is N? Well, I'll keep the chart up here for you right now. And N is what? N is 1, yeah. And what is L? L? Well, L has the value of 0. And what is the value for M sub L? Well, the value of M sub L, the only one that's available right there, is 0. Okay, and the last one? What is M sub S? What is the spin? That's a good question. Do we choose +1/2 or do we choose -1/2? I think there's something else we need to look at. We'll take a closer look at spin by looking at the right-hand rule of thumb. Now here's a right hand. Look at the way the fingers are pointed. If the fingers of the right hand are pointed in the direction that a charged body, like an electron, is spinning, the thumb will point to the north pole of the magnetic field that is produced. So if the electron is spinning like this, now wrap your fingers around it mentally. The poles are going to be a north pole here and a south pole here. In other words, what we literally have is a magnet. When it's set up like this, we call this spin +1/2. Now, if we flip that hand over and the spin is in the opposite direction, we see that the poles are situated in the opposite direction. And we call this spin a negative 1/2. It takes these two spins to have a pair of spin-paired electrons. It may be a bit of an oversimplification, but it does point out the electron's magnetic properties and the fact that when you bring two magnets together, their opposite poles are going to be attractive, their like poles are going to be mutually repelling. Why is it even necessary to consider this magnetic property? Well, we have found that if we place an element in a magnetic field, its line emission spectra will change. This phenomenon is called the Zeeman effect and was discovered by the Dutch physicist Peter Zeeman in 1896. The spin orientation, designated as +1/2, is the lower energy of the two spins. That's this one right here. Now, before we finish the electron configuration of hydrogen, let me make sure you understand something thoroughly. And that is, this whole presentation on spin is an oversimplification, but it is a model that will work well for us as we go through this course. You will deal more with this when you get into physics. Well, let's finish the electron configuration of hydrogen. We're talking about the 4 quantum numbers for this electron. And we've determined that n is 1, and L is 0, and m sub L is 0. The question we were asking was, does m sub s equal +1/2 or -1/2? And now we know that m sub s is +1/2. Now I want you to notice how we designate that. Look up here. Do you see this arrow right here? Yes. We use an arrow up to indicate a spin of a +1/2 and an arrow pointed down to indicate a spin of a -1/2. Now let's look at helium. Helium has 2 electrons. So, where do we put them? Well, remember, they can go in the 1s. The 1s can hold how many? Yeah, they go in the 1s. It can hold 2 electrons. And those 2 electrons are 1 up and 1 down, so those 2 electrons are spin paired. That's right. Now, there's an interesting thing we need to talk about here. There's a designation for this, for when we have electrons that are spin paired and when we have electrons that are not. For example, electrons that are not spin paired are called paramagnetic. Paramagnetic. And paramagnetism is the attraction to a magnetic field that will occur when one or more electrons are not paired or not spin paired. So hydrogen atoms are paramagnetic. What is the other case called when everything is spin paired? It is called diamagnetic. And diamagnetism is a slight repulsion to a magnetic field that occurs when all of the electrons are paired. There's a lab that we can do to determine how electron configurations go that use this quality of paramagnetism. Let's look at lithium. Lithium has an electron configuration. Let's see, it's got 3 electrons. So where shall we put them? Well, they go into the 1s with 2 electrons. It can hold no more, so the next one goes into the 2s and places 1 electron. And what do you know about lithium? Why, lithium is going to be paramagnetic. Let's go now to beryllium. Beryllium has 4 electrons. Where do they go? Well, 1s2 and 2s2, and everybody is spin paired. What's next? Boron. Boron with 5 electrons. Well, let's see. We should be able to build on what we were doing with beryllium. 2 electrons in the 1s, 2 electrons in the 2s, yeah. And where does the last one go? Where does the fifth one go? How about going to the 2p, going into the x, and there's one electron there. One electron. Got it? The first electron, think of it this way. The first electron going into the p orbitals, the px, the py, and the pz, defines the px. So the first one going in goes into the px. Carbon, 6 electrons. Do you want to try it? Here, take a moment and try it. Did you get 1s2, 2s2, 2px with 1, and 2py with 1? This is an example of something that we call Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. And essentially what it says is, when placing electrons in a subshell, like the p for example, which has more than one orientation, and the p happens to have 3, the x, the y, and the z, you put one electron in each orientation first. Then, if there are sufficient electrons to do so, you come back and pair them up. So carbon has 2, they're going into the p. One goes into the px, one there. One goes into the py, one there. Nitrogen has 7. You want to try it? I have 1s2, 2s2, 2px1, 2py1, 2pz1. Hund's rule of maximum multiplicity again, yeah. All right, let's go on. Oxygen with 8 electrons. Now, you're going to add one more in there to the configuration of nitrogen. Where's this 8th one going to go? How about like this? How about 1s2, 2s2? We put 1 in each of the p orbitals. Now we're going to put a second one in the px, and that makes up our 8. By the way, are oxygen atoms paramagnetic or diamagnetic? That's right, they're paramagnetic. If you have even one unpaired electron, you're paramagnetic. All right, let's look at the 4 quantum numbers for this electron right here. The 4 quantum numbers for that. Can you do it? The first quantum number is, you need some help? Here's the chart. Maybe this will help you. What are the 4 quantum numbers for this? Well, did you get 2, 1, plus 1, plus a half? Well, just to be sure you understand, let's look at where these numbers came from. The 2 comes from n. The first quantum number is the n quantum number, and in this case, it is 2, 2px1. It's 2. The second number, the 1, comes from the p. Remember that L, when L has a value of 1, then you have the shape that is the p. So that takes care of 2p. Z, that is plus 1. Negative 1 is the px, 0 is the py, and plus 1 is the pz. This is the pz, so it's plus 1. And the plus 1/2, well, right there is where it came from. It's the first electron to enter, and it comes in with a plus 1/2 spin. Got it? Now let's look at potassium, atomic number 19. We're going to jump just a bit, and we're going to group things. And if we have the P subshell completely filled, then lump it together and call it P6 if we're going to go beyond. Only if we're going to be only filling the P shell in part are we going to break it down. Got the idea? So try the configuration. What do you get? 1s2, 2s, okay, got it. So you're going along like this, 1s2, 2s2, 2p6, 3s2, 3p6. Now what? Where do you go? the 3D, or the 4s? Well, in order to make a decision about that, and I hear you saying 3D, but I want to remind you that one of the first rules of the Aufbau process is never place more than 8 electrons in the outer energy level, in the outer value of n. So in order to answer this question, we need to look at relative energies. Here we go. I want you to look at this. Do you see that as we go up 1s, 2s, 2p, 3s, 3p, 4s, look at the 4s, the 4p, and the 3d, and where they lie with regard to each other energy-wise. Do you see that the 4s and the 3d are very nearly the same energy? And first of all, that's the thing I want you to notice. The second thing I want you to notice is the s orbitals. The s orbitals are lower in energy than their corresponding pd's and f's, and that is due to the penetration effect. So because of the penetration effect, the s orbitals may be more stable. They may be of slightly less energy. There may be more attraction to the nucleus of those s electrons. So when we consider that, and we're debating between the 4s and the 3d, then what do you think should happen? And I think you'll conclude that the electron should go into the 4s rather than into the 3d. There's another factor, and the other factor that I want you to think about is called the shielding effect. You see, electrons between the outer levels of electrons and the nucleus reduce the impact of the nuclear charge on those outer electrons. It is as if those inner electrons are shielding those outer electrons from the pull of the nucleus. When we consider these factors, the result is this order of filling. Write down 1s. Now, come down a line and come over and write down 2s, and then 2p. And come down a line and come over again, indent again, and write down 3s, 3p, and 3d. Come down, indent, write 4s, 4p, 4d, and 4f. Come down, indent again, 5s, 5p, 5d, and 5f, 6s, 6p, 6d, 7s, 7p. Do you wonder why we didn't write the 6f or the 7d and the 7f? And the reason has to do with there are no atoms sufficiently large yet to have enough electrons to warrant there being a 6f and a 7d, even though as we learn more about atoms and we find larger atoms and we build larger atoms, the need will probably arise for those, unless by that time we find we must change our whole model. But that's a different story. So how is the order of filling? Well, it's like this. Do the order of filling the way I'm showing the arrows. Fill the 1s, then the 2s, then the 2p and the 3s. Fill the 3p and the 4s, the 3d, 4p, and 5s, the 4d, 5p, and 6s, the 4f, 5d, 6p, and 7s, the 5f, 6d, and 7p. And those arrows are kind of indicating where in some areas there might be some overlap, some near overlap. There's another way you can do it. You can use this rule. If you can't figure out which subshell to use, go to the N plus L formula value. For example, if two possible N plus L combinations are found, just like in potassium, use the one with the lower N plus L value. So let's look again at the electron configuration of potassium. Now, if we use this one, if we put that last electron, that 19th electron in the 3D, this is going to give us 3 plus 2 is 5. Where do these numbers come from? Well, the 3 comes from there. And remember the D? The S is 0, the P is 1, the D is 2, so the 2 comes from the fact that it's the D, and that gives us a value of 5. On the other hand, if we use this electron configuration, let's do the N plus L value for 4s, and that is 4 plus 0 to give us 4. That's 4, and the S, remember, has a 0 value, and so that's where we get 4. So that would tell us to use 4s1, but I have a feeling you'd like to use that diagram that I gave you just a moment ago. And later, when we get to the periodic table in greater depth, you will understand you can use the periodic table to do this. There's our choice. Let's look at degenerate orbitals for just a moment. Let's consider nitrogen's electron configuration of 1s2, 2s2, 2px1, py1, and pz1. See these? These all have the same energy. They all have the same degree of shielding. They are said to be degenerate orbitals. Here's something I want you to think about. Would the 2s and 2p orbitals of hydrogen be degenerate? Why or why not? Would the 2s and 2p orbitals of hydrogen be degenerate if they were occupied? The Pauli exclusion principle. The Pauli exclusion principle tells us that no two electrons may have the same set of 4 quantum numbers. Or, you might think of it like this. 2 electrons in the same orbital must have opposite spins. And remember, electrons differing only by spin are said to be spin paired. Remember? So if we look at the electron configuration of oxygen, we will see that these electrons are spin paired, and these 2 electrons are not spin paired. Now, I know we've mentioned spin pairing before, but we need to reinforce it. To give the electron configuration of osmium atomic number 76, let's see if we can do it from memory. Are you ready? Now, if you get stuck, go pull out that order of filling chart and follow along with it. But here we go. 76. Let's see, there's 1s2, 2s2, 2p6. Then we go to the 3s with 2 and the 3p with 6. Then we go to the 4s with 2. And we go back now to the 3d and put in 10. Now at this point we have done, by my count, 30 electrons. So let's keep on going. After the 3d comes what? Well, it's 4p with 6. And then 5s2. And now we go back and pick up the 4d, and we fill it, because we're not through yet, fill it with 10. Then we have the 5p with 6, then the 6s with 2. Now we go back, way back in, and pick up the 4f with 14. How many did we do on this line? There's 6, 8, 18, 24, 26, 30, 40. This is 40 on this line, so we've done 70. We only have 6 more to go. So where do we go? We've 4f with 14. Oh, we go all the way back now to the 5d. And in the 5D, we're going to put a total of 6. And how are they broken down? Do you remember that the D has 5 orientations? The D1, the D2, the D3, the D4, and the D5? Well, we put 1 in each of these, 1, 2, 3, 4, 5, and come back and put a second one here. And that gives us the configuration. This one is spin paired, and these others are not spin paired, and that's the electron configuration. Now, before long, we're going to show you a shorthand way of doing this. But for right now, practice doing it this way. There are several important exceptions to the Aufbau process that we need to cover. Let's start by looking at chromium. Now, chromium has an atomic number of 24, and you might want to pause this video and do the electron configuration according to the Aufbau process so we can use it for comparison. And then come back and I'll show you how it might have been. It might have been like this. Yes, if we follow the Aufbau process all the way through, we would have had 2 electrons in the 4s and a total of 4 electrons in the 3d. And this orientation of the 3d would not have had any electrons. But in fact, it's not that way. Do you remember earlier our having said that atoms tend to be most stable when their shells and subshells are filled, half filled, and empty? Well, look at this. Look at what we've done here on this electron configuration. We have taken an electron from the 4s, and we have borrowed that electron, and we have put it in the 3d. So that now what we have is 1 in the 4s and 1 in each of the 3ds. So that everything, the 4s and the 3d, they're all half full. And that seems to be the desirable form that chromium takes. Along that same line, let's look at copper. Now, copper has 29 electrons, and you may want to stop this and do your own electron configuration following the Aufbau process, and then come back and I'll show you what the Aufbau process would have had us do. Here's what the Aufbau process would say for us to do. Now notice, here we have 2 electrons in the 4s and a total of 9 electrons in the 3d. The 4s is full, the 3d is 9/10 full. Can you imagine a better way? How about like this? We borrowed one of the electrons from the 4s, and we put it over here in the 3d. And as a result, we now have 1 electron in the 4s and 2 in each of the 3ds. In other words, the 4s is half full and the 3d is full. And yes, that's the way it should go. Let's let you try now. Let's let you try one now. Try silver. Yeah, how should silver's configuration look? Silver has an atomic number of 47. So put 47 electrons in. Pause the video and do that. And then come back and I will show you what seems to be the best way to do that. We go along here, and I'm going to have to backtrack to get enough space. And here's the electron configuration. Is this what you found? You notice that it's going along just fine all through here and is full through the 3p. But the 5s. We had 2 in the 5s originally probably, and only 9 in the 4d. But when we borrowed one from the 5s and put it in the 4d, we came out with a half-full 5s and a full 4d. Compare silver and copper. Look at them closely. Now look at a periodic table and see where they are positioned on the periodic table. Remember that. Here's another exception you need to learn. Oh, don't get pouting about it. It's just got to be done. I want you to learn palladium. Palladium has some interesting properties. Are they related to electron configurations? It may be. Now you might think that palladium's electron configuration would be this, but look down there at the 4D. The 4D has 8. Oh, it would like 10. You say, well, I know if it has 9 in the 4D, it's gonna swap one with the 5s. Sure. This only has 8. But look at what it does. (4D10). And how many electrons are in the outermost energy level? And the answer is there are 18. Total violation of the Aufbau, I understand. But this is the way palladium is. Just learn it. Now let's look at electron configuration of ions. And most of these are going to be pretty predictable. For example, look at the sodium ion. Now first, the electron configuration of sodium is this. When it loses an electron, which electron do you think it would lose? Sure, this one right here. And so the electron configuration of the ion is 1s2, 2s2, 2p6. Or, if you will, it has the electron configuration of neon. But there's another thing you need to look at, because they don't all follow that pattern. All of the cations aren't as predictable as the sodium ion, for example. What you really need to remember is you remove electrons in order of decreasing in value. Remove electrons in order of increasing in value. And that's what we did. We took, of decreasing in value, we took the highest in value, which was 3, and we took the electron from there. Now, on that basis, what would you expect for magnesium? Well, magnesium plus 2. Here's the electron configuration. That is magnesium as the atom. So which 2 is it going to lose? And of course, you immediately went out to the 3, to the s, and you took out those 2. All right. What about the aluminum plus 3 ion? And you say, not a problem. It has a neon configuration because it's going to lose those 3s2 electrons and that 3p1 electron, and it's going to leave it with the electron configuration of neon. All right, let's go on. Transition elements may be a whole different scene, though. Let's look at some. Let's look at the Fe plus 2 ion. Do you recall I told you to remove electrons in order of decreasing in value? We'll keep that in mind here. Here's the electron configuration for iron. So which electrons are we going to take away to make the iron have a plus 2 charge? And the answer is, we'll take away these 2. All right, that works. That leaves us with argon and 3d10. Let's try another one. Let's look at the cuprous ion. Now, copper has this electron configuration, and we have to remove 1 electron. Which one shall it be? Well, yeah, that makes a lot of sense, doesn't it? We will remove that 1 electron, and now we have the argon core with 3d10. But what about the cupric ion? Now we're still dealing with this electron configuration for the copper metal, but now we've got to remove 2 electrons. This one is not a problem, but where shall the other one come from? And the answer is, it appears to come from the 3D, leaving us not with 10, but with 9 in the 3D. What about The ferric ion. We've done the ferrous ion. Let's look at the ferric ion. Here's the electron configuration for iron, and we must remove 3 electrons. Which 3 shall it be? 2 from here and 1 from here, leaving us with 9 here. This is the way the transition elements go. Try this one. Indium with a +1. Indium with a +1. Here's its electron configuration. Now what do you think? Are you going to take 1 from the 5p1? Are you going to take it from the 5s2? Well, the rule is to remove in order of decreasing in value. But there are 2 that have the same n value. In other words, there are 2 that are in the 5. So what we're going to do is add yet another rule to you. Remove in order of decreasing L value. And if we remove in order of decreasing L value, then what we do is we take this and we say, okay, which has the higher L value? Well, S is a 0 and P is a 1. So the higher L value is the P, so we lose that one. And here is the electron configuration of the indium +1 cation. Got the idea? So remember that. The first rule is to remove in order of decreasing n value. The second rule is remove in order of decreasing L value. All right. Let's look at some negative monatomic ions. Now, negative ions, generally their configuration is the same as an atom with that number of electrons. For example, consider the sulfide ion. The sulfide ion has 16 electrons as sulfur, plus it's gained an additional 2 electrons. So it has a neon configuration with 3s2, 3b4, 3p4, but it gains 2 electrons. So, if you will, it gives it the neon core 3s2, 3p6. And notice, that's the same configuration as argon. And that is typical of monatomic negative ions. They tend to have the same electron configuration as the following noble gas. Well, we've talked about a brief history of the atom. We've talked at length about the electromagnetic spectrum, and from there we developed the concept of the Bohr atom. And from that, with adjustments to the Bohr atom and to that model, we developed the modern atom. Then we concluded with the Aufbau process, a lot of interesting and highly applicable material. A better way to teach and learn chemistry.